Yeah, so let's get started with why we need thin film growth after having seen importance of crystalline growth of materials, doing authentic physical property measurements, research device applications. You need materials, solid state materials exhibiting so many different properties in a crystalline, right? Uh, so crystallinity comes in naturally if you grow a single crystal or when the material is obtained in its thin film form. So thin film technology, if you look at the technology itself, um, even though technology is a new word coined in this century, is one of the oldest technologies known and one of the newest sciences. Uh, so ancient craft of gold beating, uh, no, we could go down to the level of 0.3 microns, which means you take a piece of gold. Uh, Gold has been there since ages, right? And gold, the art, ancient art of gold beating, been there all over the world. So gold beating, even during 1500 to 1300 BC, we could achieve thin foils of gold of 0.3 microns. So to that level, you cut down the size of thickness and by just the form of beating. It's called the process of gold beating. Okay, you heat it up and beat it. You make those thin foils. You're looking at you know such small thickness of gold. And make a comparison of this to human hair. No, the diameter of the human hair is anywhere from 40 to 70 microns. Today's gold leaf can be beaten down to zero point 0.1 to 0.05 microns, which you're almost beating down gold to the nanometric level. Okay. And of course, we can also use thin film growth processes to make these nanometer thick thin films. So basically, what's the difference between a piece of gold beaten down to micron and submicron level, and a piece of gold or a gold used as a target material or a source, and then converted it in the form of a thin layer. Thin films of gold using all these sophisticated techniques, you can go down to 10 to 300 nanometers, right? You can even go down to 1 nanometer. Monolayers of materials can be grown these days on. Okay? That's why I said ultra thin films, less than 5 nanometers, and you have super lattices, these heterostructures, etc. So the dimensions are really going down. They've already shrunk down to nanometric level. That's what I mentioned. You can grow one monolayer uh, thick layers. Okay? So if you look at Moore's law, states that microelectronic industry, the transistor density doubles once in every 3 years. With generation that is 3 years. Um, you know, 3-year cycle. And if you look at DRAM, dynamic random access memory, it started with dimensionality of 250 nanometers in 1997 and reached 150 nanometers in 2001. And well, the projected one for 2010 itself, almost a decade ago, uh, was 20 nanometers and it was already achieved. So, and then the memory chips, 64 MB per square inch, 97, and then 20 GB per square inch in 2001. The projected one 10 years back was 100 GB per square inch, which was also achieved. Achieved the projected 1 terabyte per inch square in 2016 was successfully achieved. You see that this is a progression in terms of the technology. Okay. Now, so thin film technology has made a great progress in the last 3 decades. So we have, more so in the last 1.5 decades, because you have the thin film process, we have the known thin film process, known characterization tools, but then it's the sophistication that has been brought into thin film growth processes. The improvisation that has been brought into thin film growth process, and the extraordinary development in better and better characterization techniques. And combining these two, can I look at the crystal growth aspects or the crystallinity of a thin film that is being grown, which means I'm growing a thin film. I want to see if it is crystalline or not. How do we see that? You grow a thin film using a given method, and then you take the film out, subject it to diffraction study, right? You know that. But can I do an in situ measurement? This is called an in situ measurement. In situ stands for doing measurements while the process is on. The thin film is growing. I want to grow a single monolayer, a double monolayer, or 10 monolayers. At each point, at each multi-layer level, I'd like to see if crystallinity is there or not. Which means I grow one monolayer, take the film out, put it in the X-ray diffractometer, and do the measurement. Take 10 monolayers, do the measurement. But today, we have in situ measurements. During the growth process, I'm able to measure the quality of the film that is grown in a process. That's the sophistication I'm talking about. Okay. So the rapid progress in solid-state electronic devices has been possible with the development of very sophisticated deposition and characterization process, and all this has led to superior quality of thin films. In today's technology, in the last 20 years, this laptops and desktops and mobiles and all these electronic gadgets, there's just a quantum jump in the way we are able to store information, and the mobile phone itself is a great revolution. And it's all about the nano level fabrication, and that is pushing technology to real ultimate limits, is it not? Now, why thin films? It's always a question to be asked. Why thin films? Because for many reasons. You have semiconductors, you have oxide electronic materials. Examples I gave, the wide band gap systems that give rise to very interesting transparency and conductivity in materials. All these systems, when they're obtained in thin film form, you can envisage lots of applications. So semiconductor thin films offer, the 3-5 semiconductors offer a plethora of applications. The invention of blue LED that won the Nobel Prize in 2014 was its discovery to thin film process technologies that are available, because it's all about growing gallium nitride multilayers, and they have these several quantum confinement layers. It's called quantum wells, to tune the emission wavelength. All that is possible because of the advancements in thin film growth technologies, processes, technologies, and the characterization tools that can be nicely integrated to do in situ measurements. And just as you have a plethora of applications using semiconductors, 3-5 semiconductors, another class of materials, oxide electronic materials, offer ample opportunities for device applications. Resistor films, capacitor films, bolometers, sensors, electroluminescent thin film panels, wear resistant coatings, right? So it's all about how can we realize high quality thin films of multi-component systems like YPCO, barium copper oxide superconductors. Uh, uh, Even though we still don't have a room temperature superconductor, yttrium barium copper oxide in its thin film form has plenty of applications in microwave circuitry. Then you have PLZT, PZT. PZT is a piezoelectric material that has a lot of applications in most electronic devices. Right? Also, manganites, for tunnel junction. So it's all about how we realize good quality epitaxial multilayers, um, homoepitaxial layers, heteroepitaxial layers. All these terminologies you'll come across in this course. Example of tunnel junctions, quantum cascade lasers, etc. So all these different types of materials and different types of systems in their thin film forms are grown by two broad categories of growth methods. I mentioned this to you earlier: physical vapor deposition and chemical vapor deposition. Now, the typical sizes of grains in thin films. I mentioned to you earlier that the whole process of growing materials in thin film forms is to completely eliminate the grain boundaries, like what you see in the case of polycrystalline systems. Grain boundaries are a hindrance to, say, current flow through a semiconductor, and they're detrimental to physical property. So you don't want grain boundaries, you want an envisaged device application. So one way to eliminate grain boundaries is to convert these polycrystalline systems into semicrystals and thin films. In case you have grain boundaries in thin films, what this information here shows you is if you have polycrystalline thin films, they'll be more damaging than the bulk polycrystalline material itself because of the smaller grains that you have in thin film form compared to the micron-sized grains that you normally end up with in polycrystalline systems. So the typical grain sizes in thin films, if at all you have granular films, or anywhere from 0.01 to 1 micron. This in comparison to the grains, sizes of grains in bulk that ranges anywhere from 1 to 100 microns. So that's why thin films, if your method gives a polycrystalline thin film, they'll become more reactive than bulk compounds. So how to estimate the fraction of atoms associated with grain boundaries? In say, typically spherical grains of diameter Lg, the estimate is a thumb rule estimate is 6A by Lg, where A is the atomic dimension, L is the diameter of the grain. Which means to make an estimate with Lg of say 1,000 angstroms, it means you have one fraction of an atom out of every 100 atoms, and if you extrapolate it to the entire volume of a thin film, this number that means the number of loosely bound atoms in grain boundaries is going to be very large in case of thin films, which means you have more number of loosely bound atoms associated with grain boundaries, more reactivity the thin films become. That's why it's important for us to choose a thin film growth method that gives us completely grain boundary free, single crystalline epitaxial thin films. It may not be possible to get epitaxial thin films of all different types of material systems. So in which cases, if you still see grain boundaries, we might want to tune the parameters in such a way that the grain boundary widths are extremely narrow. Okay, and you also should try to eliminate twin boundaries. Well, grain morphology and orientation are very important in thin film technology. A major goal in microelectronics industry is to eliminate the grain boundaries through epitaxial growth of single crystalline centers. That's the reason why you want to grow a completely grain boundary or grain-free thin films of material systems. So if you manage to get a single crystalline thin film, it is called an epitaxial. So for that, you have special PVD and CVD techniques available. PVD stands for physical vapor deposition, and CVD stands for chemical vapor deposition. Here is an interesting comparison. What you see here is just as you must have seen aluminum foils, which are thin aluminum metal foils wrapped up around food items to keep the food hot, also fresh. Well, basically, you can use gold also, gold film, but it's more expensive, right? So if you see where are these gold films used? You know? Gold foils, or you call it gold reflective foils or reflective films, are typically used in aerospace applications. It's a very interesting aerospace material capable of reflecting 78% of all radiation heat with a continuous operating temperatures of even up to 450 degrees centigrade. So that's the reason why when you have seen the pictures of satellites before the satellites are launched into the orbit, in order that these components are not exposed to external radiation, right? The entire the interior of all these parts is completely wrapped with gold foils, right? Gold also doesn't oxidize easily, and it reflects almost 80% of radiation. It's always necessary for. So you must be wondering when you see these pictures in books and television, why these gold foils are always wrapped around these satellites and their components. It's always the case, right? Even at the lab level, if you want to protect any electronic component from being exposed, see, radiation exposure to materials, if I have a material, if it is constantly exposed to radiation, it starts losing its properties. Because radiation can create what is called radiation damage. You have how are satellites powered? Satellites are powered with solar panels attached to them. The space labs, right, which are there 100 to 400 kilometers above the ground level in orbits. How are they powered constantly? There is no problem of getting constant solar energy. So tap the solar energy using photovoltaic cells, solar cells, and use that energy to power the satellites and these experimental labs up there. But these panels, which are of high quality photovoltaics made of silicon, single crystal silicon, gallium arsenide based photovoltaics, they should last for 20-25 years. But the problem is the constant exposure to radiation, the outer atmosphere, can cause a serious damage to the material property. So you take any material, expose it to high energy radiation, ultraviolet, X-rays, and gamma rays, you start seeing the physical properties getting deteriorated as a function of. And this is, I always like to give this nice example. I don't know if you're seeing this place in Pondicherry. It's some kind of a hall they've created. It's called, they call it the prayer hall, where it's Pondicherry is 150 kilometers from Chennai. It's as hot as Chennai, humid. But then the whole idea was to create a globular structure like this, and keep the interior cool without having to use air conditioning, right? So the process is, if you have these reflectors all around, right, like that, you should be able to reflect back most of the light during the daytime. It is indeed, you can go and visit this. I think you have booked your visit time to go there. It's about 15 kilometers before you enter this place, Pondicherry. You don't have to. It's in the outskirts. It's a very interesting place. So the moment you walk in, you'll see that the temperature inside is 8 to 10 degrees less, because none of the radiation is transmitted through the walls of the structure. Because what happens is, as you see these parabolic shaped mirrors, they're all coated with shiny gold-looking coating. Well, their initial plan was to coat it with gold, but then the cost estimate was too high, so they settled down to a material like titanium nitride. Titanium nitride also, it's a protective coating. It has good reflectivity. Then it basically has, in terms of cost effectiveness, it's not so expensive. So if you want to have a micron thickness of gold, the best idea is to have titanium first on say even stainless steel, right? Because you can't afford to have a thick gold layer, and then go for a thin micron sized layer of gold on top. That's what is done there. So these are called coatings. You have a material in the form of a thin foil. You have a material in the form of a coating, right? And the coatings are several microns and hundreds of microns and millimeters thick. That's why they're called the coatings. Anything above 1 micron, or to be exact, where the crystallinity is lost, normally that happens beyond 5,000 angstroms. You start seeing the material. You can start calling the material as a thick film, form of thin film growth. So you have a thin film growth. Beyond a certain thickness, the crystallinity is lost, and then you can start calling it a thick film. And then when thickness is beyond some hundreds of microns, few millimeters, they're known as coatings. So you don't worry about crystallinity in that case. You will not see crystallinity beyond a certain thickness value. So they're all called coatings. But then what is important is the coating should adhere to the surface on which it is coated. That's very important. And so a foil of gold, right, a thin layer of some of these metallic systems. But then if you're talking about epitaxial growth, crystalline growth, and this is an example where, so you grow gold and germanium, right? Gold and germanium. What you see is, if you put the thin film after a certain, following a certain preparative technique to make these systems for microscopy, transmission electron microscopy study, what you see is the beautiful arrangement of array of atoms, atomic arrangement. That is called epitaxial thin film. But to prove that, you need to do diffraction. You also need to do microscopy. Microscopy can reveal, what kind of point defects are there at the atomic level, inclusions and then dislocation restriction. Right? Yes, this is what I was talking about. So all the titanium watches that you buy in the market, of course they're gold coated, but below the gold, so all these braces, are made of stainless steel and or brass, mostly brass, or some other alloys to prevent corrosion. So brass is not so shiny. Then you need to have this gold luster, right? How does it come? It's coated with titanium nitride, which exactly replicates the color of gold, and then you have a very thin layer of gold. So you're not expending too much amount of gold on top of base that is made of brass, right? Because if you put directly gold and brass, you need a lot of material. You may have problem with adhesion. So you need to have sometimes these interlayers before the final layer comes in. You see how many things you're seeing in this slide, right? Material in a foil form that has applications. Material in a coating form, right? Coatings has applications. And materials in completely epitaxial form. This has a large number of applications in synchrotron sources, etc. You can use them as thin film gratings. Yes. The grating, obviously, you have well separated atomic levels, atomic arrangement of atoms. So this can be used as a grating. Now coming to the vacuum system, this is one of the oldest transparencies that always use it. I'll explain in a more clear way as we go along. But basically, vacuum system consists of a vacuum chamber and lots of vacuum components. So you have a vacuum pumps on this side, chamber on the other side. You have vacuum gauges. So it's a whole business of knowing how to create vacuum, maintain vacuum, and read vacuum. That's very, very important before you start learning what happens in the chamber that you see above all these modules. Okay? What you see is a TC gauge, roughing valve, backing valve, etc. Yeah, this is a very simple, not so sophisticated lab-made. Is made by a company, of course, with some of the components that we can always assemble. You see that exactly what I've shown as a sketch. This is called the bell jar. It all started with the bell jar technology. It's just a glass dome. Okay. So something like this one. It is exactly like so glass dome. Okay. So you put it on a flange here. Put it on a this is a flange. Okay. And there's a hole there, and you start evacuating it using the pumps beneath. So that is your complete pumping market. And these are all the bellows connected to these are all tubes. See, these are all tubes connected to the vacuum pumps. There is one vacuum pump there. This is the main vacuum pump that is called the diffusion pump. Diffusion pump and rotary pump work in tandem. And you see, you have all these valves that have to be operated in a specific sequence before desired vacuum is achieved inside the chamber. It's all very important. All these operations are very important. Finally, so the whole operation happens inside the chamber. You have the source. Because you see, if I want to grow a thin film of a metal, so I have I keep the metal inside, and I just can't heat it without the vacuum, because if I heat a piece of metal, silver evaporates. It forms a thin film on substrate, which is kept a few centimeters above it. But that may not be the silver film, because the silver atoms, when they move towards the substrate on which they get deposited, they also pick up oxygen from the surroundings, and so you get a nice silver oxide film, which is an insulator. So that's the reason why you need to remove all the air molecules from the chain. So it's very important. Okay. Yeah. So the vacuum chamber, that's a vacuum chamber. This is a pump. In simple terms, it's a chamber. Of course, these days the chambers are prepared in a very sophisticated way, with different types of metals that can withstand high enough vacuum levels. Because these bell jars, the chambers made of glass, which is okay for normal vacuum operations of 10 raised to -5 to -6 bar, but not you cannot generate. They can't withstand extremely high vacuum levels. That's where you need metallic vacuum chambers. But the basic concept is the same. You have the vacuum chamber. You have a set of pumps that serve the purpose. Okay. You see that? Lots of, this is what I've shown there. Typically, so I can have a flange here, a flange like this, right? So this flange has a hole to connect it to the pump beneath, and it has a small pressure measuring gauge that will tell me what is the vacuum created inside, and it also has to have a O-ring, a gasket. That's it. Right? Once the suction happens, if this surface is smooth, you'll be able to retain its position without. I mean, you can't even remove it easily once the vacuum is created. Okay. You see that this typical bell jar there with a small what is called a rotary pump. You can create a vacuum of 10 raised to -2 torrs. These can be home designed. These designs can be done at home, and this is, as you see, a more sophisticated modern day vacuum chamber. Okay. See that this is made of metal. These are strong metal flanges. The flange has to. That's see. You can always have a leak at that point, right? At that point. So this is connected to a flange. This flange sits on top of the vacuum pump assembly, and that's where the leak can happen. So these are the chambers are actually very heavy, and otherwise good vacuum cannot be created. And today the chambers have lots of additional peripheral things, because you also would like to see what is happening in a glass dome. When the evaporation is happening, I can see what is happening inside, right? I can at least see the source being melted, then the deposition also happening on the sides of the walls, if it is not directional. So in some cases, in process like sputtering, you'd like to see what is happening inside. So there are lots of flanges, for connecting different devices. As I told you, I'd like to even today you can do diffraction on the growing film. That's what I told you in the beginning of the class. Will I be able to assess the quality of a growing film? So I grow one layer, two layers, three layers, and then what is the crystallinity of each layer? Oh, instead of taking the film out at each stage, which is not easy because to build up vacuum itself, it takes a lot of time. Now imagine I have an in situ method by which I see diffraction. This is called a very interesting method called REED. It's called REED. RHEED stands for reflection high energy electron diffraction. So to do that, I need to also incorporate an electron source and a detector. All that is possible in today's chamber designs. All are custom made. Then you have ports for several of these vacuum meters. There are Pirani gauges, pinning gauges, low vacuum measuring gauges, high vacuum measuring gauges. They're all not the same. The thermocouple gauges. And if you want to have to measure high vacuum, you need to use ionization gauges, right? It's a whole lot of process. So all that now you see, it's a regular chamber. This has no other connections. The only connection it has is beneath, right? But then in today's modern day chamber, you have lots of these additional ports for temperature sensing, for pressure sensing, the viewports. There are also other tools. You want to have probes. You want to, if there is a plasma generated during the thin film growth process, and you also want to measure the plasma characteristics. I can do it today. So I can insert a probe inside or near the plasma. I can do the time of flight measurements. After all, everything is a time of flight process, right? The atoms are emanated from the source or target, and they move towards the substrate. And during that flight, you should be able to find out, this is called the time of flight measurement. Okay. So the chamber design is becoming more and more sophisticated. Now, let's see how all this has started. It's really interesting to see or estimate the so-called, power of vacuum, right? The power of vacuum. The best example to start with is with the Magdeburg hemispheres. Yeah. What are these hemispheres? So that's a hemisphere called the Magdeburg hemisphere. It's a 4-inch hemisphere with which some very interesting experiments were done on. Imagine it's like you have a coconut, you break it into two halves. Exactly, you see a hemisphere like that, right? So this can be fabricated at the lab level. You have a hemisphere, and you have an attached pipe-like structure, and you have a small valve. Obviously, you understand why that is there, to suck the air out. The other part is also closed, right? This was designed in the 1870s, but today's, if you call it a pipe connected to a vacuum component, a vacuum chamber, you don't want the pipe to have this shape, You want the pipe to have smooth interiors. But gas molecules or air molecules are not trapped inside. So the Magdeburg hemispheres were basically designed by a German scientist who was also a mayor of Magdeburg, which is a place in Germany. He wanted to demonstrate the air pump that he had invented and the concept of atmospheric pressure and how you reduce pressure from a given enclosure. You see, that was his interest. So he came out with this wonderful concept of using two hemispheres. So the full assembly looks like that, right? These are made of, hot iron. There's strong pieces of iron, right? With the interior, of course, hollow. You can imagine when you bring both of them together, so that's where if air is sucked out, you should create so-called vacuum inside. That's a simple concept of vacuum. Okay? And you can see that. So this is a air suction mechanism that means you drill a hole there in one of the hemispheres, connect this small tube with a valve-like mechanism whereby you can open and close. You understand why that is so? Because now if I connect it to an external air suction mechanism, right? After sucking the air out, before you disconnect the suction mechanism, the vacuum pump, you can just close it, right? So that the pressure, the low pressure that you've created inside should stay there if there are no leaks here. So where can the leaks come from? The leak can come from that area because these two are two external bodies connected together. And also this is sort of an additional connection that is coming, right? And of course, these parts, they have to be nicely finely welded. And you have sort of two folders, two hooks there. So you can imagine what he wanted to demonstrate was when you have two hemispheres connected together, you take air out, you create vacuum, very small vacuum levels, low vacuum levels, not extremely high vacuum, right? Because with a normal suction pump, you can't create a vacuum more than 10 raised to minus 1 torr, and it's 2 torr at the maximum, right? Now, what happens when what he demonstrated was very interesting. So, you can imagine that now you connect it to an external pump, you take that's what he had invented, no? It's air pump, right? So, when you have, air pump is very simple concept. When you have a rotating shaft that throws air onto you like a fan, and the same fan is used as an exhaust fan also, right? It can also suck the air out. Basically that. So this is a pictorial represent. There's no photography there. This is a pictorial representation of what he actually demonstrated to the public at that time. So this is a very interesting, nice picture. What you see is that's the Magdeburg hemispheres assembly, this assembly with those two hooks. So after creating vacuum, after air molecules have been sucked out with the air pump, right? He wanted to test the strength of this connectivity between these two hemispheres by connecting horse carriages on both sides. It's amazing, right? That's what it is, right? See? And then he made them, pull them to different directions. And see, this is how physics experiments were demonstrated in olden days, right? They also did some crazy experiments. There was long back a similar note. One scientist wanted to do an experiment. He wanted to see the head-on collision impact of two trains, two locomotives. He wanted to show to the public how powerful that impact would be. So he made all the people assemble around the tracks, and then two locomotives running at each other, face to face, head on, moving at 50 kilometers per hour. They were made to collide. So the impact was so bad that obviously, the debris flew around, and there are many people, the um, audience, died. These are crazy experiments, but this is a nice experiment to show that, well, you have a small two hemispheres connected together. You remove the air out. You can try that. You just can't pull it with hand, even with 5 people on this side, 5 people on that side. So we wanted to demonstrate how powerful the assembly of these hemispheres would be, the Magdeburg hemispheres, even when they're pulled using cars. That's what. So you can estimate the power required to uh, remove these two spheres separately. So that's a power of vacuum. So when you create vacuum, even a low-level vacuum with no leak at that point, it's impossible to remove it unless you went in air through it, right? So the easiest way to remove those parts is the way you have removed air. You also push in some air so that the lock is removed. All right, so yeah, so the growth process is very simple, right? So that's what it is. So I'm using a chamber, a simple form of chamber. This is called a chamber. Uh, in the olden days, it used to be called the bell jar. Today, we call it a chamber. If it is a physical vapor deposition method, if it is a chemical vapor deposition method, you call it a reactor. Why it's called a reactor? Because in chemical vapor deposition, you normally see reactions happening on substrate. So a simple thin film growth processes, of course, you need to have pumping modules. Normally, this pumping is a combination. These pumping modules are a combination of low vacuum creating pump and a high vacuum creating pump, and they work in tandem. Something like a rotary pump creates a initial low vacuum that is called the 4 vacuum. And then the more sophisticated pumps take over, like the diffusion pump, turbomolecular pump, or cryo. Right? So that's where the vacuum pump assembly is very important. And this is an ideal design. What you're seeing is the vacuum pump directly connected to the chamber. In reality, this is not the case. So you have the vacuum pumps, 1, 2, or 3 of them, and they're sitting somewhere else, and you have all these vacuum tubes connecting to the pump, and all the suction is done by them. And that's where the complexity comes. How effectively you can use those pumps using those connecting mechanisms, pipes, tubes, in order to get the best vacuum level. So you might have a good vacuum chamber and very sophisticated pumps, but if the connecting mechanism is not proper, right, you'll never get vacuum inside the chamber. So you have the vacuum chamber. The simplest of vacuum processes is thermal evaporation, and which means I take in the case of thermal evaporation, we start with a charge or a source, aluminum, copper, silver, gold. Thermal evaporation is still a very interesting method by which you can get thin layers of metals and alloys. If I want to create a thin layer of how do you make mirrors? The mirror is basically glass, and it has silver coating on one side, right? If you can afford to have a silver coating, it's fine, or you have a fine aluminum coating that gives the reflecting aspect of. So all these elements can be obtained in their thin film form. So you just use the source, heat it up, and to its melting point, what happens? The material vaporizes, evaporates, and the vapor is collected on the substrate that is kept there. This is the simplest of processes that is called the thermal evaporation process. But thermal evaporation process is a low energy thin film growth process, and it is the process also is non-directional. That means the vapor that is rising from the source, when you take it to its melting point, all the heat is used in melting the element, right? So you will also see the deposition happening all over the place. That's the reason why if you are using the bell jar and for thin film growth, after several depositions, you see the interior of this bell jar is coated, and the, the the transmittance of this bell jar decreases. So you need to clean it up if you want to have better visibility to see what is happening. Okay. So that's the simplest process. That's why I said if you have copper, aluminum, silver, gold, especially these three elements, if you do not remove the air molecules before you start heating it up, what happens? You get, because everything is at the atomic level, you atomize it, you melt the element, and the vapor is rising. And in that process, it can also react with the gas molecules inside the chamber, right? Is it not? And so if air is present, if you're not taken out air molecules can react, the oxygen and air molecules can react with these elements, and you see the formation of aluminum oxide, copper oxide, and silver oxide. So you're not getting a metallic film, but you get the metal oxide film. But that process is also required if you want to make a reactive thin film. Suppose you want to get a silver oxide film, then you also have oxygen present inside the chamber to get silver oxide. If you want to get a nitride film, so I use a chromium source, a metallic chromium, and during the evaporation, I also have nitrogen inside the chamber. So I make the reaction to happen. So I get chromium nitrate film. So that's called the reactive thermal evaporation, which is a very common way of producing compounds in thin film. Okay. Yeah, this is a substrate, and ideally, no, the thin film grown on the substrate. Then, of course, you need to see. So all thin film depositions, the characterization measurements, not only thin film growth processes like physical vapor deposition process, a number of them are there: thermal evaporation, sputtering, molecular beam epitaxy, laser deposition, atomic layer deposition. All these physical vapor deposition methods and some chemical vapor deposition methods also require vacuum or some sort of reduced pressure environment. Not only thin film deposition process, you also need vacuum for characterization tools, especially spectroscopy measurements, right? X-ray, photoelectron spectroscopy measurement, electron microscopy, right? Microscopy and spectroscopy require vacuum. You can't do measurements without the presence of vacuum in the measurement chamber. So vacuum is required not only for thin film growth, but also for physical property measurement equipment, like most of the microscopy and spectroscopy techniques, right? So that's where, even though the process looks simple, the complication comes from the way you need to design these pumps, the way you need to design the chamber. So there has been a tremendous progress, as I told you, in the last, especially in the last 2 decades, in terms of powerful vacuum pumps that have been that are available now, and beautiful new kinds of chamber designs. Today, you can think of having a vacuum chamber of the size of a room, right? Say your hostel room. Can you imagine that whole room is used as a chamber to grow a large number of thin layers or thick layers, right? What kind of applications? Want to have coatings on, say, compact discs, several coatings, and these coatings have to be done on a large number of batches. The industry cannot afford to do coating on one or 10 or 100 pieces at a time. So there's a requirement to create large area chambers, and also, which means you need to have pumping modules which should deal with such big chambers. There are parabolic mirrors of the size of 1.5, 2 meters used by space agencies, right, for various experiments. And now this whole 1.5, 2 meters of parabolic mirror has to be coated with protective layers, reflective layers, and all. So you can imagine the chamber size. You can imagine the amount of time that it takes to create a vacuum. So the calculations that go into um, having the right kind of vacuum pumps to create ducts out of vacuum inside those chambers. This all becomes challenging. That's where the vacuum science leading to vacuum jet technology become. Vacuum science is a very important component of thin film workplaces. Okay, so I think about that.